are in generalized linear models with examples in R, and we're still in chapter 3, question 325. Okay, here we go. So we're looking at a data set that is called ratliver. The basic idea is that it's experimental data where rats received some kind of drug, were given some kind of drug, and then they looked for how much of that drug found its way into the liver. And there's some hypotheses here, anyway. But what's important for us is that the amount of drug that a rat received was a function of their body weight. Okay, so you weigh the rat, and then you convert that to some kind of dose. Okay, and so we're going to go through and ask a bunch of questions and try to answer those questions. Okay, so the first thing you need to do is to install the GLM's data package, load it with library, get the data, which is in GLM's data package. Here I'm calling it D, and we can see the first few rows of it, right? So we see that our variables are body weight, liver weight, dose, so the dose they receive, which again is a function of body weight, and dose in liver. Okay, so after they looked at their livers, they found this much of the drug in there. Okay. So the first thing that we're asked to do is to plot each variable. I've already done this. To plot each variable, or to plot dose in liver, which is the outcome, against each explanatory variable. Okay, and so that's what we've done here. So here we have body weight against dose in liver. Here we have liver weight against dose in liver. Okay, and here we have dose against dose in liver. Okay, so I'm not sure what one would pick up immedately by looking at these. After we go through the entire problem, you might come back and say, oh, okay, well, maybe there's a pattern here, but to me, nothing jumps out that's important until having gone through the rest of the question. So I won't comment on anything important there because I don't know what's important yet. Okay, so now we're going to fit a linear regression model, dose in liver against the other three variables. Okay, so you can do that. With LM dose, and then use a period, and that gives you all three of the other, all the remaining variables in the data set. So we run that, and then we're supposed to, in part 3, use t-test to show that body weight and dose are significant for modeling dose in liver. So we do that, and let it think. Okay, and sure enough, we see that body weight is significant and dose is significant. Okay. Now, in part 4, it says, in the study, the dose was determined as an approximate function of body weight, which we've already stated. Hence, both variables, body weight and dose, measure, about the same quantity, they carry the same information, presumably. Why should both covariates be necessary in the model? By computing the appropriate statistics, show that observation 3 has high leverage and is influential. Okay, so the phrasing of this question is a little bit confusing. It says, why should both covariates be necessary? And this either seems like, oh, they should both be included, why? Or it seems like this is a rhetorical device to say, why are we doing this? And trying to demonstrate that we should not be doing this. Okay, so I don't really know how to take that, but nevertheless. So I'm going to answer it as though they're saying that we should. So here's my answer. So the answer is I don't know. But one possibility, having worked with mice and rats in this kind of a setting before, is that there could be quite a bit of measurement error, right? You're putting these squirming rats onto a scale, and they're moving around, and sometimes it's hard to get a really good weight. And then you're having to draw up some drug into a little syringe, and it's always kind of an eyeball thing. You're doing as best as you can, but now you have two, you're measuring two things, both with error, and you're trying to make one that, one's a function of the other, and so on and so forth. So it could be that there is enough measurement error that it just is beneficial to have both of these in the model. Okay. So, so, so in other words, even though they carry a lot of the same information, two variables carry a lot of the same information, the amount of error means that they aren't carrying identical information. Okay, so one thing that we can do that we've done in the previous couple problems here, so I'm not going to expand on it, but we could just, what have I done here? We could install the CAR package and use the VIF, the variance inflation factor, for everything. Okay, and so that's what I've done here. So I've done a couple things. First, I've plotted dose against body weight, and then isolated observation 3, and then I've looked at the variance inflation factors here. Okay, so we see that body weight and dose do indeed carry a lot of the same information according to VIF. Okay, but I don't really know what to think about that yet. And then if I plot body weight or dose against body weight, there is a very nice relationship here. But when I isolate observation 3, it does kind of fall off the beaten path a little bit. And so it could be that that this guy, observation 3 here, rat 3, accidentally received a little bit too much. Now, the next part of the question is we're supposed to show that observation 3 is highly influential, has large leverage, etc. And we can see that here. I don't know how well you can see it, but there's an observation rate here, that kind of surpasses, our Cook's distance boundary that starts to qualify something as an outlier here. So again, you could go through and find the actual hat values, etc. But these plots do a fine job here. Now, in part 5, we're supposed to plot dose and body weight. I've already done this, and so here's observation 3, and so now we're supposed to fit a linear regression model. Just clear this for a moment, but without observation 3 to see what happens. Okay, and now when we do this, now we see that that these coefficients are no longer significant. Okay, and that the variance inflation factors are way, way up. They were high before, now they're really high. And so apparently error, a dosing error or a data recording error was the problem here. So, okay, we'll call that good.